Okay, so people on Zoom can hear me, right?
Yeah. Yes, Sajjan.
Okay, good. So yesterday we enjoyed the exam, right? So we have three problems. The first problem is on formulation of optimization problem, right? So the objective is, well, students must be able to demonstrate the ability. Okay, you must demonstrate the ability to formulate an optimization problem to solve a chemical engineering problem, for example. Okay, so this is 10 points, right? So you see from the question, a chemical company produce three products, A, B, and C, using two raw material. You have two raw materials, R1 and R2, right? You don't care. You don't have to pay attention. What is it? What are R1 and R2? Okay. Also, the product also, we have three products, A, B, C. Okay. And the company wants to optimize its production plan over the next 4 months. We are dealing with multi-period optimization problem, right? We have 4 periods, of course. And to maximize profit while considering varying market demands, raw material availability, and storage constraint. Okay, so given the first one, production capacity, 500 tons a month total for all product. Okay, so this is production capacity. Oh, wait a minute. Should be 500 tons. Oh, this one is not clear. Okay, 500 tons per month for all product or for each product. Anyway, if you treat it as a sum of our product for 500 tons is okay, or you treat as each product 500 tons, it's okay. Both are okay. Okay. And raw material consumption are here. Okay. So what does it mean? In order to produce 1 ton of product A, it requires 0.5 ton of R1 plus 0.3 tons of R2. Okay. It shows requirement of R1, R2 in order to produce 1 ton of product A, product B, also product C. And you have raw material availability. The R1, R2, okay, in each month, you have different availability limit. Okay. For example, the first month, you can use up to 400 R1, 400 ton of R1, and 350 ton of R2. Okay. And the next one is product demands. For product demand is shown in this table. For example, first month, the market can absorb 200 tons of A, 150 tons of B, 100 tons of C only, okay? You cannot sell more than that, okay? Because it's over demand. And storage capacity, 200 tons for each product. Initial inventory, 50 tons of each product. Storage cost is $10 per ton per month for each product. Oh, our product is really cheap, right? Only $10 per ton. And production cost per ton, yes, this is, and selling price per ton. Okay, now your task. You must define the objective function to maximize the total profit over 4 months period. Okay. If you can define that, you get 2 points. Okay. So what is the objective function? The objective function maximize total profit, and profit equals revenue. Okay. subtract by production cost and storage cost, right? Anything else? No. What is revenue? Revenue, you know, you sell not all the product you produce are being sold at certain months. Okay? Because you produce, let's say, even you produce 100 tons, not all of them will be sold at that month, right? Because you're going to plan for 4 months. Okay? So you need two variables, two class of variables. The first one is production. And the second one is the amount of the sale. Okay? And the revenue is calculated by what you sell. Okay? The products, well, so at selling at each month, we have, because the cost, no, the price of the product is totally different, right? Different for A, B, and C, so you have to separate it. So 1000 SAI plus 1200 SBI plus 1100 SCI. Okay, S is standing for sell, the amount of product being sold, and what is this? A is product A, right? And subscript I means, well, month, right? Which month? Okay, then move to the production cost. For production cost, you know, the cost for production, okay, for each product. So the variable P is standing for production, okay, the amount of ABC produced at each month. Okay. Okay, again, I is month. Okay, and because the cost for production of A, B, C are different. So 500 for A, 6. Why we need this one? Oh, this is, you should remove. Yeah, this one, this parenthesis must be removed. No need that parenthesis in front of 600. Okay, 600 and 550 for C. Okay, and the next one is storage cost. So this one is depends on how you set up your variable. If you set up T as inventory of product X at the beginning of period I, then you don't need the first one, okay? Because at initial inventory, you don't have to pay anything, right? Okay, so it's 10 TAI plus 10 TBI plus 10 TCI, just that. Okay, so we declare these variables. This is a variable. I is a time period, right? Which month? S is sales of product X in period I. Okay. PXI, production of products X in period I. And TXI, inventory of product X at the beginning of period I. Okay. If you define your TXI as the inventory of product X at the end of period I, is okay, no problem. But you have to change, yes, the I here is running from maybe from 1 to 3, yeah. And what about this variable? This variable inside here, okay? This part, this variable here. Sales of product X in period I, production of product X, inventory of product X, okay? Where X are A, B, and C, okay? And I running from 1 to 4. The next one is constraint. We have a lot of constraint. So it's deserved for 3 points, okay? Because it's longer, it takes more time to write than objective function. And So we have production capacity, okay? This one. Or you can write PAI plus PBI plus PCI must be, no, this lesser than, sorry, this must be lesser than or equal, okay? I will share it later. Not greater or equal, lesser or equal. Sorry. This must be lesser than or equal. Okay? And the next one, raw material availability constraint. For raw material availability constraint, you have to determine R1, R2 for each month. Okay? Okay, from the first table, right? From the first table, I think. Yes, from this table, right? For example, R1 equal PA times with 0.5, right? And PB times with 0.4 and 0.6 of PC. Okay. You see, you have R1, R2, okay? And for different months, okay? For 4 months. The next one is demand satisfaction constraint. For demand satisfaction constraint, of course, all the cell must be less than what given in the table. Okay. And the next one is inventory balance constraint. Inventory balance constraint is the heart of multi-period optimization. What we produce for product X at each Y. Oh, okay. Move out. From product X, okay, at the first month minus what we put on sale at that month, subtract what we left in the inventory for the next month, equal what we have in the stock, okay? And because we start from 50, right, initially, so it just you can add it this side. What we produce, what in the stock plus 50, right, on the left hand side. But I already moved that plus 50 to the right hand side. Okay. It's okay. You can add 50 on the left hand side and then put 0 on the right hand side. No problem. Okay, that is the first month. And the second month is what we produce plus what left in the inventory at the beginning of that month minus what we put on sale minus what the remain, okay? What we left in the inventory for the next month, okay? For the first month also follow the same, okay? And the last month, what we produce plus inventory at the beginning of that month, we minus by what we put on sale must be less than 200, okay? Why we put 200 here? What is the meaning of that 200? Yes, it's storage capacity, right? You cannot produce more than that because it's going to waste. And storage capacity must be between 0 and 200, okay, for each variable. No, not each variable, each t variable. Okay, and then we need non-negativity here. Okay. Okay, then you can, for D, you can list of some assumption. For example, you don't have to list all of these. Anything you can imagine, you write down there. Okay, for example, constant selling price and production cost over the planning horizon. Okay, because we assume that, right? Linear production cost, no economic of scale, perfect demand forecast. Okay, no back order allow continuous variables, no setup times or cost for switching between products, instant raw material availability at the beginning of each period, no quality deterioration of stock products, sufficient production capacity to meet all demands, for example. Okay, you can list one or two of it. It's okay. Also, E, benefit of solving this multi-period optimization problem. Of course, you can read some reason why we solve this problem. Okay, maximizing or solving this problem would benefit the company operation by maximizing overall profit across the entire planning horizon, optimizing production schedule to meet varying demands efficiently, balancing production and inventory to minimize storage costs, ensuring effective utilization of raw materials, especially when availability varies, providing insights for capacity planning and raw material procurement. Okay. Okay, any questions? Okay. Any questions? No. No, then we move to question number 2. This one. Well, the objective for this problem is you must demonstrate the ability to solve a convex optimization problem. Okay. I expect that, well, you can demonstrate that. And for the Bloom taxonomy for this problem, it's analyze. Okay. The previous one, it's create. Okay. Okay, so the problem is you must be able to analyze this kind of problem. The question is, consider the following convex optimization problem. Yes, it is convex. Minimize this objective function, x1 square plus 2x2 square plus 3x3 square. Okay. And subject to x1 plus x2 plus x3 equal 1, x1 plus 2x2 lesser than or equal 1. Okay. And x1, x2, x3 must be non-negative. Okay. And your task. Okay. You get 4 points from formulate the Lagrange function. Okay. Okay, for this constraint, you have one equality constraint, one inequality constraint. Okay, quite simple. And derive the KKT conditions. Okay, KKT conditions include stationary, prime unfeasibility, dual unfeasibility, and complementary slackness. Okay, and then you must solve the problem. Okay, by using KKT condition, derive. Okay. And I emphasize here that make sure to explain each step in your solution and verify. The important is verify the solution satisfies on KKT conditions or not. Okay. And C is interpretation, 2 points. Okay. You must discuss whether the solution found is optimal, whether it satisfies all the given constraints. Okay. Explain why the solution is valid within the context of convex optimization with both equality and inequality constraint. Okay, so the solution Lagrange function. Okay, you start from objective function plus lambda times with equality constraint. Okay, plus mu inequality constraint. Right? Okay, and for KKT conditions, the stationary condition, because the derivative of Lagrange function respect to each variable must be 0. Okay, for x1 you get 2x1 plus lambda, right, plus mu here equals 0. Okay, and the next one, the derivative respect to x2, 4x2 plus lambda, right, lambda plus 2 mu must be 0. Okay, and the third one, derivative is 6x3 plus lambda equals 0. Okay, what about prime unfeasibility? For prime unfeasibility is nothing, it's from original constraint, because we need this condition because any solution we obtain must satisfy this primal feasibility. Okay, if it's not, that is not our solution. Okay, and dual feasibility, mu must be greater than 0. Okay, and the next one, this is important, complementary slackness. From inequality, mu times with this inequality constraint must be 0, right? The condition that force mu or this one, this active, this constraint active. Okay, if this constraint is active, we don't care about mu. Okay, however, if this constraint is not active, mu must be 0. Okay, okay, so you get 4 points from derived by solving this condition or this condition. You obtain the same result. I recommend you start from complementary slackness. You have two conditions. Mu is 0 or this one is 0. Okay. Once you obtain the first way, mu, when mu is 0, okay, you substitute mu 0 here and here. Okay, and you get 2x1 plus lambda 0, 4x2 plus lambda 0, 6x3 plus lambda 0, and x1 plus x2 plus xt is 1. Okay, you have 4 conditions. You have 4 variables, x1, x2, x3, and lambda. Okay, you solve it. It's linear, right? It's very easy. However, this one, the what is it? The solution obtained, you must check with primal feasibility. And unfortunately, that solution does not satisfy this primal feasibility. Okay, you can do it by yourself. Okay, and what about the other way, where this x1 plus 2x2 minus 1 is 0? Okay, you can solve it again by using this condition, and this x1 plus 2x2 minus 1 is 0. Okay, and by solving that, you obtain this solution. Okay, yes. Because the mu is negative. Oh, sorry, it must be lesser than this one. This one. Your solution is mu is positive, and you obtain the same equation.
ทำตัวเหมือนกัน
ถ้ามันเหมือนกันน่าจะเหมือนกัน
ต้องมากกว่า
น่าจะสลับกันมากกว่า เดี๋ยวเช็คอีกทีหนึงว่าเป็นยังไง let me check again about this. However, once you substitute back to primal feasibility, this solution is totally fine. Yes, it should be okay, but tell me one thing, that your solution, this constraint is active or not? This constraint is active or not? If it's active, it should be okay. But I don't think that. Yeah, this one should be, the first one should be active always, right? You can substitute it back. 5 and plus 2 is 9. 9 by 9 is 1, right? But this one, the question is this one is active or not? If it's not active, mu must be 0, right? I don't know. Did you check again? I will check. You remember your solution? Yes, you can do it now. Whether this one is active or not. Your solution is 1 0 0. It's active or not? 1. Yes, it's active. Yes, if it's active, it's okay. Right, 1 plus 0. Yes. And what about other condition? What lambda? What lambda is it? Lambda and mu. Mu2. No, you cannot have different mu. You need only one mu. This one? Then you have 4 mu then. Okay, if you have 4 mu, it's okay. But the KKT condition, you get the same this. Oh no. Yeah, but you have to check with this one also. Stationary condition is stationary point or not? Okay, so back to your x1 plus lambda minus 1, right? And you plus mu1 x1 plus 2x2 minus 1. Okay, and you plus mu2 x1 plus mu3 x2. Right? Okay, so then you, oh, this is correct. You obtain different stationary condition, right? From the first one, it's 2x1 plus mu 1. No, plus lambda mu 1 plus lambda plus mu 1 plus mu 2 equals 0. And 4x2 plus lambda plus mu 1, no, 2 mu 1 plus mu 3 equals 0. And this one is 6x3 plus lambda plus mu 4 equals 0. Yes, it's okay. And you need, oh, you need mu 1, no, x1 to x2 plus x2 x2 must be 0 or minus 1 also, yes, plus 2x2 minus 1 must be 0. And mu 2 x1 must be 0. Mu 3 x2 must be 0. Mu 4 x3 must be 0. Okay, and in your case, because you got this 0 0, then mu 3 and mu 4 are not 0, right? Except this one, mu 2 is 0, right? Yes, you have to check this one also. If it's okay, then it should be okay. Okay. Okay, so C, convexity of the objective function. Then this objective function is a convex quadratic function. We have square of x1 plus something square of x2 square of x3. So this one, if we check Hessian matrix, okay, is positive definite for sure. And therefore, any solution satisfying the KKT condition will be a global minimum, not just a local one. Okay. And the KKT condition are necessary and sufficient for optimality in this context convex problem. The KKT condition include the following. Complementary slackness. The inequality constraint is either active or the Lagrange multiplier mu 0. And we found the solution, and this solution satisfied. Oh, okay. This one I have to check again. The Lagrange multiplier mu is greater than 0. We got here it's mu less than 0. So we have to check this. Okay. Now, because no, actually you don't Hessian because of this. Just one moment. This objective function, the what is the Hessian of this one? No, just the objective function. We have 2, 0, 0, and 0, 4, 0, right? 0, 0, 6, right? This is our Hessian. Okay. And this is positive definite for sure. Yes, it's positive definite, so it's convex. Yes. So this case, any points on this objective function is convex. Okay. So let me check the what is the objective function, objective value of the objective function. Your case is 1, right? And this condition is less than 1, right? Because this is smaller than 1. Square of this one is less than 1. That's okay. Okay, one moment. Let us use, oh, this is 3 variable. We cannot draw it. At first, I thought that I can draw the surface, but no, impossible, because we have x1, x2, x3. No, it's okay. Okay, now we move to problem 3. Solve the linear programming. And this one, the learning objective is demonstrate the ability to solve a linear programming problem. Okay. And this one again, evaluate. Okay. The question is, you are tasked with solving the following linear programming problem using simplex method. And the problem must be solved by hand. And all steps must be shown clearly. We have 4 variables. Okay. And we have 3 constraints. Okay. And luckily that all constraints are can be handled by just phase 2. Okay. Your task, solve the linear programming by hand and use the simplex method to solve step by step, and introduce slack variable to convert inequality to equality and provide a final optimal solution. Show our intermediate Tableau calculation and clearly identify the pivot elements, and evaluate and interpret the result. Okay. So this is the first table. This is the first table. And this is the pivot element. Okay. From this table, of course, you can use row operation in order to make this pivot element to be 0, to be 1, right? To be 1, and other row in the same column must be 0, 0, 0. Okay. We obtain this. Okay. And the next pivot element is here. Okay. That means in the first iteration, we introduce x3 as our basic variable, and we remove s3 out, and then this x2, right? We introduce x2 to replace s2. And then we arrive at this table, okay, which is only two iteration. Yes, this is the third iteration. Mhm. And the optimal solution is x1 is 7.35, x2 is 15.59, x3 is 6.76. Okay. Okay, and this is the optimal objective value. Oh, sorry. Yeah. ครับสวัสดีใช่ครับอ๋อ Okay, so for B, evaluate and interpret the result. So you must resolve the problem again. Maybe it takes time. Okay, but it's okay. Just only 2 points. If you don't have enough time, you can skip this part. Okay, but what you're going to do is you must change the right hand side here. Side. Increase the right hand side by maybe 10. Okay, 1 or 10 is all right. And then solve the solution and see how the objective function change. Okay. For example, here, if the right hand side change from 60 to 61, okay, only 1 unit, and the optimum objective value change 1.45 units. Okay. Okay. And we check constraint too. Again, we increase the right hand side by 1 unit and see how the optimum objective value change. Okay, it changed by 6.47. Okay, and constraint 3. Okay, the sensitivity is 7 point something, 7.65. Okay, we increase the right hand side by 1 unit and then see how the optimum objective value change. Okay, so we can conclude that the constraint 3 is sensitive. Okay, the right hand side of the constraint 3 is sensitive to is the most sensitive one. Okay, sensitive to the change of the optimum value of the objective function, right? Okay, if you choose for investment, if the company is considering investing in the capacity expansion, they should prioritize addressing the third constraint, okay, because it's sensitive to the objective value, okay? Okay, just that. So I have to check the second problem again, okay? But don't worry if you obtain different solution, but that solution satisfying the constraint, it should be okay. The KKT condition, it should be okay. Any questions? Any questions? No? For online, any questions? Allow me 5 minutes. One moment. Okay. Now we back to our mainstream. All right, so we're going to discuss about nonlinear programming. So the basic of nonlinear programming is, you know, you learn one trick to solve the optimization problem. I mean, both convex and non-convex, nonlinear, right? For linear programming, is very easy. You can use simplex, okay? But normally no one use that because you can solve it using Excel, right? Also, you can use it, solve it using Python because we have library already. We don't have to solve it by hand, okay? But for nonlinear programming, the tools you have now is KKT condition or Lagrange condition, right? Derived from KKT condition or Lagrange condition, you can solve analytically, okay? It's not numerically, right? But anyway, KKT conditions are still useful for us, okay? What we learn is, for any solution, any feasible solution, if we test it with KKT and it passed the KKT, I mean, it's satisfying the KKT, that point can be a solution, our solution, right? Right? That point can be our solution. Why? Because it's already passed the KKT. It means that condition is okay. The next thing is, previously you obtain solution by analytically, you solve it by hand, right? The problem is, for very complex problem, you cannot solve it by your hand anymore. For example, you have 10 constraints, 10 decision variables, right? Now the question is, the problem is, how can we solve it? How can we solve? How can we obtain the candidate solution? Okay, because once you obtain the candidate solution, it's all right. You test it with KKT and everything is all right. Okay. So in order to solve it numerically, you know the difference between numerical and analytical, right? Analytical, well, you derive those equations and then you solve by hand. For numerical, you don't analyze all these variables, but you start from some numeric value, and then it's evolved to other value is all right. Okay, and you obtain some numeric value, right? Some number, and you test it, you got that solution. Okay, so the basic idea is first, initialization. We start with the initial feasible solution. This is the must, okay? We start from any point, no matter that point, as long as it's feasible point, no matter it's satisfying KKT or not, yes, but as long as it's a feasible solution, yes, we can start from that point. Then we follow iterative process by evaluate the objective function and then adjust the variable, the different variables in a way that seeks to improve the objective function. Okay. You start from one feasible solution. Okay. And you try to evolve that point, that solution to the new point with having smaller, I should not say smaller, better objective function. Okay. And remember that we have to adhere to the constraint. Okay. Then what does it mean? We start from feasible solution. We evolve it to the new feasible solution, having better objective function. Okay. If we are going to minimize it, we are moving in a direction where the objective function is smaller. Okay. Or if we maximize it, it should move to the point, feasible point, new feasible point, having higher objective function. Okay. We repeat the second step, step 2, until we reach the stopping criterion. Okay. We call it termination. Okay. For termination, the process, which process it is? It's an iterative process. The process stops when no significant improvement can be made to the objective function, or when a preset number of iterations are reached. Okay. Normally, we have two conditions to stop. First, we cannot further improve the objective function of that point. Second means or when, well, we reach the maximum iteration number. Okay, we will not run forever. Okay, we stop at certain point. So what is the challenge with nonlinear programming? First, nonlinear programming can be quite challenging due to the nature of nonlinear function, where there may be multiple local optima. Okay, because we don't guarantee that in the region of interest is a convex function or not. For convex function, you don't have to care about multiple local optima, right? Because for convex function, you only have one local, okay? One local optima, that means optimum, that is global optimum also, okay? And the next one for the challenging issue is the landscape of the function can be much more complex, okay, with rich valley and saddle point, okay? And again, we never have saddle point if our function is convex, right? If our function is not convex, then we will suffer from rich valleys and saddle points. And the next thing is mathematical properties that help in linear programming, like convexity may not always be present in nonlinear. Okay. The tools you have in linear are not available here. Okay. Again, from the basic three step, from including initialization, iterative process, and termination. Okay. We can translate into more detail. Okay. From that basic idea, first, we start from initial trial point. Okay. What we need from initial trial point? X1 must be feasible solution, right? Must be satisfied on the constraint, okay, in the feasible region. And then we find suitable direction that points in the general direction of the optimum, okay? And then find appropriate step length for movement along that direction, okay? I will explain you again in detail. Then we obtain new approximation, new point, x. We start from xi, right? This is x1, and then this iterative process, we start from xi. And then in the direction, we define with the appropriate step length, we obtain new point, xi plus 1, okay? Then you test whether this new point, xi plus 1, is optimum or not, okay? If xi plus 1 is optimum, then we stop the procedure, okay? Otherwise, set a new I equal I plus 1 and repeat step 2 again. Okay, so now we look into more detail of the direction and the step length. What does it mean? Imagine that you are in the wood, in the forest. You don't know where to get to the valley. Okay? And you initial point, okay? At one certain point, what information available to you at that point? While you are located somewhere in the wood, in the forest, what information available to you? And you want to go down to the valley. The very, very basic one. The slope. You want to go down to the valley. You will not step uphill, right? Okay. So this is the direction you should follow. Go against the uphill, go downhill, right? So you find the slope. Okay. This is in practice. Okay. In mathematical sense also, what is standing for the slope? It can be derivative at that point, right? The derivative must be, well, you should go down, right? Okay. Once you have one direction, okay, you define the direction you want to follow at that step. This is direction, SI, okay? You find the vector or the direction. The next thing you have to design is how far we should go, okay? How far we should go by following that direction. Because you don't know, you want to go to valley, but you don't know what happened in the after you go beyond 100 meters, let's say. Okay, so you should find the longest part that you can follow that direction. Okay, and then you we will reach new point. Okay, once you reach new point, you test against the optimum. The new point is optimum point or not. If not, you find new direction again. And you determine the step length again. Okay? And you see this algorithm, you can, what's it, develop new algorithm based on this idea. And the algorithm we recently, we use today is based on this idea. Okay? But they have different way to find a suitable direction. And also they have different way to find appropriate step length. Okay. And one more thing. Imagine that our objective function is 5 dimension, for example. You have 5 decision variables. In this step, find suitable direction. You define the vector, right? Okay. You determine the vector that you want to follow. And the next step is you find the step length. Step length actually it's one variable. It's scalar. That means we, what's it? We translate the original optimum objective function having 5 variables into a new objective function with only one variable, because this is only one variable. It's step length. Okay. So, for example, this one, we're going to minimize this objective function. Okay. We have only 2 variables because higher dimension I cannot draw it anymore. Okay, so we start from x1 here. Okay, we find the direction. The direction can be this direction or this direction or this direction. Okay, any direction. Yes, this direction, this direction, this direction is all right, as long as the direction lead to the new point having smaller objective function. Okay, you don't have to follow the, what's it, steepest descent. The steepest direction may not be a good direction. Okay, and once you find the direction, you calculate or estimate the lambda. Lambda is step length. What does it mean? You see that this direction, if you follow this direction, it can move you from this point to any point along this direction, right? And if we go too large, I mean large step size, what happened? What happened if you go very long step length, move to the other side? The objective function will not decrease, but increase again, right? Because it's moving up at the other side of the valley. Okay? Okay, so we find appropriate step length. Not too long, not too short. Okay? What happens if you you use too small step length? It takes forever to run, right? If you go very small step length. Okay, so once you reach this point, you test it against the stopping criteria. The algorithm should stop or not. And one way to test whether you're going to stop the algorithm or not, can you suggest it? Can you recommend some condition to test? One condition is KKT. Yes. And test the objective value also. If the objective function here improve large enough from here. Okay. All right. One, you reach here, but you decided to continue because the stopping, you are not satisfied the stopping criteria. We have to find the direction, new direction at this point. Okay. In this figure, we follow this direction. But of course, you can go this direction or this direction, but not this way, right? Because it's going up here. It's possible, right? But here we follow this direction. Then you repeat it until you reach the optimum point where KKT is satisfied. Okay. What else besides KKT? The objective function does not improve anymore. Okay. Oh, is it raining outside? Yes. I need hard rain and then stop. Okay. Once we finish the class. Yeah, we need heavy rain now. Yes. And then stop. Once our class stop. Okay. So you see that the algorithm, the efficiency of the algorithm depends largely on the lambda and SI. Okay. It depends on how efficient you find the direction and step length. Okay. Okay. Now we have lambda and SI, right? Lambda I and SI. We focus on lambda I first. Okay. Assume that we have very good algorithm to find the direction. Okay. We're going to deal with the direction later. Okay. Maybe next week. This week, we're going to discuss about step length first. Okay. How to find the new point. Okay. There are two classes of the algorithm. The first one is, we call it elimination method. And the second one is interpolation methods. For interpolation method, assume that we have one point and then you find new point using interpolation algorithm. Okay. And for interpolation method, it can classify to the algorithm which require no derivative. Okay. And the other class is the algorithms requiring the derivative. Okay. And it can be cubic or direct rules like Newton, quasi-Newton, or second method. Okay. And what about elimination method? The idea of elimination method is totally different. For elimination method, assume that we have area of interest. And then from the area of interest, if you want to find the optimum point in that area of interest, you can eliminate the part that does not contain the optimum point. For example, you have area of interest in the range of 0 to 1, okay? You know that there is a minimum point between 0 to 1, okay? The idea of elimination is you reduce the area, okay, by eliminate some area which you are quite sure that that area does not contain the minimum point, okay? So for elimination method, it can be heuristic search, exhaustive search, well, so many algorithms. But anyway, I will tell you the basic idea of elimination method first. Imagine that we have a unimodal function. You know, unimodal function, right? A function fx is unimodal function. Unimodal function like convex function. You know that in that area, there is only one minimum point. It's unimodal, not multimodal. What is multimodal? It's a non-convex where, well, you have multiple minimum point. Okay. Okay. So if we have fx, which is unimodal function, if the first case, we know that x1 is less than x2, okay? And less than x star. It's implied that fx2 must be less than fx1, okay? And the second case, when x2 is greater than x1, but less than x star, it implies that fx1 must be less than fx2. What does it mean? What does it mean? The first one I want to ask you to confirm whether you get the idea of unimodal function first. Unimodal function, convex function is one example of unimodal function, okay? But unimodal function it's a superset. For example, this one is clear that this is convex, right? What about this one? The B. B is unimodal, but is not convex, right? What about this one? This one also, right? Because we have a discontinuity here on C. Okay, so these things are unimodal function. Okay. Okay, from the definition of unimodal function, if we test x1 and x2, from 0 to 1 is our area of interest, okay? And we test against x1 and x2. We sampling x1 and x2. And x1 at x1, we obtain f1 like this. At x2, we obtain f2 like this. If in the area of 0 to 1 is unimodal, Can you tell me that which part we can safely remove? Which area we can safely remove? Which area is it? We can ensure that our minimum point will not rely on that part. X2 to 1, right? Right? Because it cannot come back again this way. But we don't know whether the minimum point lies here or here, from 0 to x1 or x1 to x2. Okay? Because it can be like this, right? Or it can be like this. What about B? For B, which part we can remove? Yes, 0 to x1. What about C? We have F1 equal F2. We can remove 0 to x1 and also x1 to x2 to 1, right? Minimum point lie here for sure. Okay, so you see that we start from 0 to 1 in the first iteration, and we need to test 2 points. We can reduce the area of interest, right? Here, this is for A it's 0 to x2. For B it's x1 to 1, right? And in C case, this is the best case where we can, well, reduce 50% of the area. Once you reduce the area in the first iteration, what are you going to do? What are you going to do in the next iteration? You can test 2 points again in this area, right? And then eliminate some part. Okay? And then you repeat it for several iterations. The area of interest is become smaller and smaller, right? Then you get some solution. Okay. This is the explanation of that. We have a interval of 0 to 1 with 2 function evaluation, F1 and F2. If the outcome is that F1 is less than F2, then the minimizing X cannot lie in the right of X2, okay? Then the new smaller interval of uncertainty is 0 to X2. And if F1 is greater than F2, then we discard some area. We discard the area from 0 to x1. Okay, a new smaller interval. It's x1 to 1. Okay, and if we have f1 equal f2, then well, the new interval is x1 to x2. Okay, that is the idea of elimination method. Okay, I hope that you can link between elimination method to the big picture, to our big picture. I mean the line search. Okay, remember that for line search, we define the direction first, right? And once the direction search, okay, it becomes a line from the surface, becomes a line. And then we find a new point, right? You use elimination method to find a new point. based on that line. Okay, so yeah, the next one is search with a fixed step size. This is the most elementary approach. We use a fixed step size and move from initial guess point, okay, to find new point. We assume the step size of S, okay, define x2, which is x1 plus S, okay, and find F2. Then you have F1 and F2, right? And then you can compare between F1 and F2. Okay? You compare between F1 and F2 like this. Then you get a new point. Okay? This is the whole algorithm for heuristic search. So the drawbacks of this heuristic search is first, inefficiency. The method becomes computationally expensive as the dimensionality of the problem increase. Okay? Also the accuracy, okay? Because you work with area, not a point. Okay? You work with interval. And the other thing is we have problem on local and global optima. Okay? If in that direction is not, you cannot guarantee the convexity of that line. Of course, you may have multiple local optima in that region. Okay, then, for example, assume that our original objective function may be multidimensional, 2 variable, 3 variable, 4 variable, whatever it is. Then we fix the direction with specified direction. It translates the objective function into one variable. Okay, one variable. And that variable is lambda, which is our step size. Okay. And then we're going to find the new point based on that. Okay. We choose the step size of h equal 1. Okay. So we find the area of interest, the length, the interval of interest, and then compute f lambda. Okay. Of course, you can work with 2 points only. Okay, but this one is fixed step size, and then we work with multiple points. Okay, can you tell me which area, which interval we can remove if we guarantee that this function is convex function? And of course, it's convex function, right? It is convex. Hmm? You see that we have this area from -3 to -3. And what does it mean? How does it look like? How, let me draw this line. Hey, website มันชื่ออะไรนะ GeoGebra ตัวแปรเดียว Okay. So this this is how it look like. Okay. So minus 3. Okay. Of course, here it's no, and maybe my calculation is wrong in the slide. What happened? 0 is minus 3. Minus 1 is 0. No, minus 1 is not 0. Right? So 1 minus 2. It should be minus 4. Sorry. Okay. Mm. So which area we should keep from here to here? Okay. From minus to 0, right? Okay. And from minus 2 to 0, you reduce the step size and evaluate again. Okay. So the area, the interval becomes smaller and smaller. Okay. Okay, then you can do it by yourself. You can do it for a few steps of this problem. Assume that just one moment. Let me check the interval first. From 0 to 4. Maybe quite starting from, okay, we must use, because this is fixed step size. Okay, do it in Excel. Maybe it's good to use Excel. Okay. Any questions? No? Okay. Okay, we can go like this. From go down from 0 to 4, right? I test it from 0 to 2. Okay. There's only one iteration now. Okay, so you see that by using a fixed step size, it's very simple, right? But the main drawback lies on the, what's it? It's computationally expensive. Okay. So it involves large amount of computational time. Okay. So, and if we have to repeat that for several steps, it's quite troublesome because it's consume large power. The next one is search with accelerated step size. Okay. For this one, the, what's it? The step size change. Okay. Through the time. You start from x0 and then choose an initial step size first with scaling factor of alpha greater than 1. Okay. Then we evaluate the objective function f at x0 and x0 plus delta x. Okay. And if the function is being minimized, and then we test f x0 plus delta x must be less than f x0. Okay. Then we guarantee that we are moving towards the minimum, right? So then we double the size of delta x. Okay. By delta x is alpha delta x. Okay. And then we update the point again, x0 plus delta x. Okay. And repeat it. And if once with this delta x, the new point, if the new point is greater than the initial point, what does it mean? It means that you already passed the minimum point, right? So you have to step backward. Okay. For example, we have objective function of x squared plus 2x plus 5 over the range of -5 to 5. Okay. Let's start from x0 is -5. Okay. And then initial step size delta x 1. Okay. And scaling factor of 2. We evaluate f x0 and then evaluate f x0 plus delta x. Okay. You arrive at this point. test the objective function as this point, and then it's 8. But for f x0 is 10, right? Then we can further repeat that step. Okay, the next one is exhaustive search. For exhaustive search, let's say that the initial interval we have from xs to xf, okay? Then it depends on the number of points you're going to evaluate from the initial point interval of xs to xs, xs to xf, right? So the length for the interval of interest is xf minus xs. Okay? You divide it by, because you use endpoint, no, an interval. So each time you can, no, sorry. The final interval of uncertainty is given by, from the starting point, once you pass, you repeat it for, no, it depends on the point. If you use endpoint and interval equally, you distribute an interval equally, it means that the next step, the interval of interest starting from L0 will be reduced to 2L0 over n plus 1, right? Here, for example, from xs to xf, and we decided to evaluate 8 points in this interval. Okay, so the number of, what is the number of the interval? 9, right? N plus 1. Okay, so by evaluate n point, we remove most of the area, but we keep at least 2 interval, right? Because, for example, in this case, you have to keep all these, right? This area, these 2 interval, right? You cannot eliminate this or eliminate this. You have to keep both intervals, right? Because we don't know exactly where the minimum point is. It might be, well, somewhere between x5 and x7. Okay, so you see that we keep 2 out of n plus 1, right? So we keep from L0, from 1, right? We reduce the area of interest to the fraction of 2 over n plus 1. Okay, so you see that if we increase the n, what will happen? If we increase the n, we can, in a single iteration, we can largely reduce the area of interest, right? However, we have to trade off with computational power because you evaluate more, right? Okay. So it's trade-off between the time used for calculation and also the area. Okay. Okay. Can you do the exhaustive search on this function in the interval of 0 to 5? You can specify n by yourself. Okay. So it depends on the number of n you use. Okay. Here I use how many n? 9. Okay. And well, you can reduce the area of interest. We know that our optimum point lie here, and then we reduce the area again and again and again. Okay. Okay. So any questions? Any questions? Yes. Hmm? No, it's not. This one we don't use step size. We define the number of interval. Huh?
Depends. We take anything.
Anything must be integer, of course. No, it's you can use 100, but I said, well, if it's 100, you have to evaluate this 100 point, right? And if your what's it objective function is very expensive to calculate, then you have problem. Okay. Okay, any questions? Okay, the next one is, we call it dichotomous search. For dichotomous search, we specify x1 and x2. Okay, it's based on delta. We need only 2 experiments. We need 2 points, evaluation points. Which is at the center. Let's say the same. Our starting interval is L0. Okay, from XF to AF. Okay, it's L0, right? So we focus at the center, at the middle. And the middle is L0, half of the L0, right? At the middle. Okay? And for the dichotomous search, from 0, you move to the left. This should be left, right? Yes, to the left. Delta, half of delta. And you move to the right, half of delta. Okay? And instead of evaluate the middle point, you evaluate x1 and x2, which is the move from the average, moved from the center point to the left and to the right. Okay? And that 2 points, it's delta difference. Okay? So you have to define the delta. It's arbitrary number. And from dichotomous search, the new interval will be reduced, but not half. It's reduced to L0. No, half of L0 plus half of delta. Okay. And if you repeat it for an experiment, I mean, you repeat it in time, the interval will be reduced by this expression. Okay. Yeah. You can try with this example using dichotomous search. Okay. Okay, and this is an example. We have, because our interval is from 0 to 5, right? L0 is 5, okay? And we have to specify delta. Okay, so we evaluate delta, no, L, half of L0 minus half of delta, and half of L0 plus half of delta here. Then you repeat it again and again, okay? Okay, the next one, the next algorithm is, we call it interval halving method. In this interval halving, we exactly, well, remove 1/2 of the interval at the current iteration. Okay, so for example, we have L0 from A to B. Okay, we divide it into 4 equal parts. Okay, then we label x0, x1, x2. Okay, I can show you in this picture. Okay, we have A to B, right? The half of it, it's x0. Okay, and x1 and x2. Okay, then you evaluate. X0 is the midden point, and quarter interval is x1 and x2. Okay, then we evaluate fx at each point. Okay, you have A and B, right? Half of it is x0. You evaluate f0, and midden point between A and x0, we label x1 and evaluate f objective function. So it is f1. And the midden point between x0 and b is x2. We evaluate objective function at x2. We call it f2. Okay. And if the results look like this, what are we going to do next? We remove x0 to b, right? We keep a to x0, right? Okay. And in the next step, you don't have to evaluate the midden point, right? You need evaluation at the midden point between a and x1 and x1 to x0 here. Okay. And you repeat it again and again. Each iteration, you will remove half of the original area. Okay. Okay, this is the first case. And if the result looks like this, of course, you remove this part. Okay. Because it's impossible that minimum point lies around here. Okay. And this is another case where f0 is the smallest. Yeah. Here you remove this part from A to x1 and x2 to b, right? Okay. You see all the possible cases, we can remove 50% of the original area. Okay. Okay, you can repeat this one. Okay. You can do it by yourself, okay, at home. Then it will improve your understanding about the algorithm. Okay, this. Okay, I move quickly because I think it's, well, you need more time to, yeah, do it by yourself. So I introduce you different method, right? Exhaustive search, dichotomous search, interval halving. Okay. And you see, this is the formula. Okay. And what happened once while we repeat it for 5 times. Okay, how fast the area of interest shrinking. Okay, okay, so we finished the first half of today's lecture on elimination method. Okay, for elimination method, you see that what you need evaluation of the objective function. Okay, you don't need derivative, right? You don't need slope, you don't need anything like that. Okay, so now we move to the interpolation technique. For interpolation technique, it's totally different from elimination method. For elimination method, of course, you have area of interest, the interval you interest, and then you shrink it down smaller and smaller, right? However, for interpolation method, you start from one point and you try to find the minimum point on that line, on that direction, okay? So if this is, the first one is quadratic interpolation method. For quadratic interpolation method, the idea is, while you try to map your objective function as a quadratic function, you don't know exactly the behavior or the shape of the objective function, but you going to estimate it as quadratic function. The good things about quadratic function is you know exactly where the minimum point is, right? You know quadratic function, right? Quadratic function is square ax squared plus bx plus c. Okay, so all you have to do is to map the original objective function, which is it's a function based on that step size, right? As a function, as a quadratic function. Okay, once you estimate the objective function as a quadratic function, then you know the minimum point. Okay. Okay, so how can we map our objective function as quadratic function? First thing, of course, we need 3 points. Okay, if we don't use the slope or derivative information, you need 3 points because we have 3 parameters a, b, and c. Okay, in that interval, you start from lambda a, lambda b, and lambda c. Okay, you evaluate that 3 points, obtain fa, fb, and fc. Okay, and then approximate that if the objective function is quadratic function. Okay, so the quadratic function looks like this, right? Okay, you substitute lambda a and fa, lambda b and fb, lambda c and fc, right? Then with 3 relations, 3 conditions, and 3 parameters a, b, c. Okay, you can find a, b, c. And this is ABC. ABC. Okay, we write explicit function of ABC as a function of FA, FB, FC, lambda A, lambda B, lambda C. Okay, it's look like this. And the minimum lambda is minus B over 2C. Okay, so we repeat it here. With this function, you see that it's not quadratic function, right? But we're going to estimate it with quadratic function. Okay. With quadratic function, you need 3 points. A, B, C. Okay, lambda A, lambda B, lambda C. And you evaluate FA, FB, FC. Okay. With this information, you can calculate A, B, C. Okay. And the minimum point is minus B over 2C, right? That is, yes, you repeat it again and again, then you can find the solution. Okay, the next one is cubic interpolation method. For cubic interpolation method, instead of estimate the function as quadratic function, you estimate as cubic function. Of course, for cubic function, you need 4 parameters. Okay. And normally, if we don't use 4 points to evaluate in order to estimate that, to calculate that 4 parameters, to determine that 4 parameters, we can use 2 points with derivative. Okay, you have 4 conditions, the same, right? But only 2 points. The objective function value and the derivative of that, of those points. Okay, then we can calculate A, B, C, D based on that 2 points, information obtained from that 2 points. Okay, and this is the minimum point. Okay, you can try the same example with this algorithm. Yes. Okay. So what we have learned so far is about interpolation method. The first one we estimate as quadratic function, right? The second one we estimate the objective function as cubic. Okay. Now we use Newton method. Okay, consider the quadratic approximation of the function first. Using, but this time we use Taylor series. For Taylor series, if any function, objective function, we use Taylor series and we approximate using quadratic term. Okay, we use lambda I as fixed point. Okay, we have linear term, right, with derivative information, and second order derivative with quadratic term. Okay, square there, right? So this one, we approximate the original objective function as this quadratic function again. So what is the derivative here? The derivative here is, yes, derivative at this point, which is 0, right? Because this is the fixed point. What about this? We have f prime here, so it should be f double prime. No, sorry. We have f prime here, right? So derivative of it becomes lambda, so it should be 1, right? So this term, the linear term, becomes the first term in the derivative, right? And the quadratic term, what about quadratic term? The quadratic term is yes, 1/2, right? The half of it of the second order derivative time with lambda minus lambda I square. Okay. So once we find the derivative, all these term becomes constant. And we have square here, so it's cancel 1 second here. Okay, so we obtain this constant, the second order derivative, and this term lambda minus lambda I. Okay, and at the stationary point, this f prime lambda must be 0. Okay, okay, it's a condition, necessary condition. So you rearrange this expression, you obtain lambda I plus 1 as a function of lambda I. Okay, so lambda I plus 1 equal lambda I minus ratio of f prime over f double prime at lambda I. Okay, so you see that starting from lambda I, we can estimate the next point by using this equation. Yes, by using this equation. And it's called quasi-Newton method. No, it's Newton method actually. What about quasi-Newton method? The point is, Newton method, we need derivative function and also second order derivative, right? And most of the time it's difficult to find because you need analytical method. Okay, and if we replace this one information of derivative and second order derivative with numerical value, okay, we approximate it by using numerical method like this. Okay, we approximate it by using numerical method. We call the result method as quasi-Newton. Okay. Yes, you can do it by yourself. Okay. The same example. Okay, then it's finished for today. Yes. Delta lambda should be small number, but not too small. It's close to 0, yes, but if you choose very small, too small for computational, you will have problem. Because why? Because once you divide it by some value which is very small, you have problem for computational. Okay, so in practice, you choose small number, but not too small. Okay, so any questions? Hmm? Yeah, all what we learned today. Yes, but this is only half of the what's it algorithm. Remember that the for the big picture, for the whole algorithm, we need direction, right? To map the original objective function into step size. Okay, from multi-dimensional to single variable, and then you find the step size, and all these elimination method and interpolation methods can be used to find the new point based on that objective function. Mhm. Okay, so if you don't have any question, then we call it there. Okay. Yes, yes, because I did that, right? I show you, but I lost all those five. I don't know where I kept that file.